Hi everyone, welcome back to my channel. Welcome back to my series Learn with Me Data Science. I am Vanshika Verma. This video covers the part neural network. So, a neural network is a machine learning model inspired by the human brain, composed of layers of interconnected nodes that process and transmit data. It's a powerful tool in data science for tasks like image and speech recognition, natural language processing, and predicting modeling. Neural network can learn more complex pattern in data and make accurate predictions or decisions. So now let's move to the Python implementation of neural networks. So here is the code for neural network. In the first part, we are importing library and preparing the data. So we are first implementing the TensorFlow library and assign it the alias TF, and we are importing the sequential model of the TensorFlow Quasar API, and then we are importing the dense and flatten layer from Keras API, and then we are importing the MNIST dataset from TensorFlow Quasar API, and then we are importing the classification report function from sklearn. And now we are loading and processing the data. So xtrain ytrain xtest ytest is equal to mnist dot load data. Loading the MNIST dataset and split it into training and testing set. Normalize the training data by dividing it this line under normalized data. Normalize the training data by dividing each pixel value by 255 and test equal to test x test divided by 255. Normalize the testing data by dividing each pixel value by 255. Then here we are printing the shapes of training and testing data using the f string. This code sets up the environment, loads the MNIST IST dataset, normalizes the data, and print the shape of the training and testing sets. So here is the brief of the output, in which training data shape is 60,028 and 28, in which 60,000 is the number of training image, 28 is the height of each image in pixel, and width of 28, this 28 is the width of each image in pixel. Now moving to the testing data shape. In this 10,000, 28 and 28 are 10,000 are the number of testing image, 28 is the height of image in pixel, and this 28 is the width of each image in pixel. So the MNIST dataset has 60,000 imaging training image, each 28 by 28 pixels, and 10,000 testing image, each 28 by 28 pixels. These images are grayscale handwritten digits from 0 to 9 that will be used to train and evaluate a neural network model. So now let's move to the defining the neural network architecture code. So here first we have model definition, in which model equal to sequential, and all this part creates a new sequential model in which flatten input shape 2828 adds a flatten layer to the model, which takes the 28 cross 28 input image and flatten them into a 1D array of 784 elements. Specify the input shapes of 28 and 28. Now dense 128 activation ReLU adds a dense fully connected layer to the model, which has 128 neurons layers to the model, uses the ReLU rectified linear unit activation function, and dense 10 activation softmax adds another dense layer to the model, which has 10 neurons unit corresponding to the 10 digit classes, which is from 0 to 9, and uses the softmax activation function, which output a probability distribution over the 10 classes. Now we in the model summary function, this function uh, Print a summary of the model architecture, including the number of layers, the number of parameter in each layer, and the output shape of the layer. So we have output in which uh, the model has three layer: flatten, dense, and dense one. The flattened layer has the output shape, which means it takes 28 cross 28 input image and flatten them into a 1D array of 784 element. The first dense has the output shape of none 25 at 128, none 128, which means it has 128 neurons and it has 140 480 parameter. The second dense has an output shape of none and 10, which means it has 10 neurons and it has 1290 parameters. The total number of parameter in the model the total number of parameter in the model is 101 and 770, which takes up approximately 397.54 kb of memory, and all 101 770 parameter are trainable and there are non-trainable parameters. Overall, the model summary provide a concise overview of model architecture and parameter. Now moving to the third part of the code, which is compiling the model. In this week, we are doing the compilation of the model. So model.compile compiles the model which prepare it for training. It has parameter in which optimizer.adam specify the optimization algorithm to use during training. In this case, it's ADAM optimizer, which is a popular stochastic gradient descent algorithm. Loss equal to sparse categorical cross entropy. Specify the loss function to use during training. In this case, it's the sparse categorical cross entropy loss, which is suitable for multi-class classification problem where the classes are manually exclusive. And matrix accuracy, specify the evaluation matrix to track during training. In this case, it's accuracy matrix, which measures the proportion of correctly classified samples. By compiling the model with this parameter, we are telling it to use the ADAM optimizer to update the model weight during training, minimize the sparse categorical cross entropy loss function during training, and track the accuracy metric during training and report it as a performance measure. With the model compiled, we are now ready to train it on our dataset. Now moving to the evaluating the mode part of the code, in which the topic is training the model, in which history equal to model dot fit train the model that on the training data and returns a history object that contain the training and validation metrics. The parameter are x train, y train, that are training the data and labels. Epochs equal to phi number of epochs to train the model for. In this case, the model will be trained for phi iteration over the entire training dataset. And validation data equal to x test, y test, the validation data and labels. The model will evaluate its performance on this data after each epoch. By training the data with this parameter, we are telling it to train on the x train and y train data for phi epochs, evaluate its performance on the X-test and Y-test data after each epoch. The history object returned it by the fit method will contain the training of and validation metrics such as loss and accuracy for each epoch. We can use this object to visualize the training and validation metric and monitor the model performance. So some common metric that are tracked during training includes are loss, accuracy, validation, loss and accuracy. So we can access these metrics from the history object and use them to visualize the training process. Now moving to the next part, which is evaluating the mod part of the code, in which first we have test loss, test accuracy. Model evaluate at text y test and x test and y test. Evaluate the model on the test data and return the test loss and accuracy. Now we have print f test accuracy. Print the test accuracy with two decimal places. Now we have y pred. So now we are prediction and classification. We are doing prediction and classification report in y pred model dot pred x test uh, argm max x is equals to 1. Here we are making a prediction on the test data and convert the output to class label by taking the argmax index of the maximum values along axis 1, and then we are printing classification report which include metrics such as precision, recall and F1 score for each class. This code evaluates the model performance on the test data and provide a detailed classification report which can help identify areas where the model is performing well or poorly. The classification report includes the metrics such as precision, recall, F1 score and support, which we are discussing in our previous video. By examining this matrices, we can gain a better understanding of model strength and weakness and make adjustment to improve its performance. So now move to the next topic, which is move to the next part of the code, which is visualizing the result. So, firstly, we are visualizing test images and with predictions. So, firstly, we are importing the matplotlib library for plotting and a numpy library for numerical computation. For we are using here we are using loops through the first 5 images. Plt.im show displays the test image using matplotlib mi show function with grayscale color map. Plt.title sets the title of the plot to include the true label and predicted label, and at the last plt.show displays the plot. This code visualizes the first 5 test images along with their use labels and predicted labels. By examining these images, we can get a sense of how well the model is performing and identify any potential issues or biases. The plot will show the grayscale image, the true label for the y-test array, the predicted label from the y-pred array. By comparing the true and predicted label, we can evaluate the model's accuracy and identify area for improvement. That's it for the video and for the code also. We have studied here a neural network, and we are demonstrating application of neural network using Python. In my next video, we will understanding the clustering part. That's it for the video. Meet you in my next video. Till then, keep smiling, keep exploring. Bye bye.